Good morning, friends. This is Professor A.k.chaubey. Professor Chaubey's physics class under the heading Physics Made Simplest. Dear friends, today I am going to discuss some more details of AC circuits involving only capacitance, then R and L combination, and then continue to R and C combination, R and C combination, etc. etc. So, I have completed AC applied to resistance only, applied to inductance only. While this is now a circuit where we have AC source, E is equal to E naught sin omega t. Omega is the angular frequency, that is 2 pi ft. This is connected across the capacitor C. So we want to see the behavior of capacitor C when it is connected with the AC source, that is E is equal to E naught sin omega t. So what is given is, we can write the capacitance C across which we have a potential source E is equal to E naught sin omega t. This is alternating AC because there is a frequency omega. So this gives the AC source connected to the capacitance C. Now what the behavior of the capacitance to the AC source? We have connected, say, so that E is applied, the EMF is applied, and then current starts flowing. The capacitance becomes charge increasing. So you know that the PD across the capacitor, potential difference, PD across the capacitor, that is, or capacitance is the same thing. The PD across capacitor will be, say, Q over C, where Q is the charge. Q is the charge at any time, at any instant. So what the charge? Q over C is the voltage there. And you know that E is the time varying, so at any time, say, E is the potential. So if E is the at any time, we cannot say E just here. E is equal to Q over C, and you know that E is the time varying, so E naught sin omega t is Q over C, the charge over the potential. So Q is equal to, therefore, Q is equal to here E naught C sin omega t. Okay? Or you can write, say, I. I is the current. Current I is what? Current I. The rate of flow of charge. So current I is dq dt. dq dt is the current I, that is differential of Q, and Q is this, of course, E naught, E naught C sin omega t. So this is the current I. Well, you can write the current I as this is say E naught, and you can have it in differential of this sin omega t. This is omega cos omega t. So this can be written as, you can write this as C constant outside, E naught constant outside, the C is constant, C E naught, and sin ddt of sin omega t, that means omega into E naught cosine omega t. That means you can write now, say I is equal to, so I is equal to E naught, and cos omega t means C omega, cos omega t means sin omega t plus pi by 2. So this means that I is equal to E naught. I can write this omega c as E naught over 1 over omega c. If I write like this, it is the same thing. And sin omega t plus pi by 2. So what is the meaning of this expression? Say I have some earlier expression. I can name numbers these expressions. So what number you will? Earlier I have not put any number here. So this was potential here given by say 1, and this I can write say equation 2. This means that E is the potential applied, and I is the current in the circuit given by E naught over 1 over omega c sin omega t plus pi by 2. Here sin omega t, here sin omega t plus pi by 2. So phase difference of pi by 2. We have seen in the inductance it was minus pi by 2, means it was lagging. Here the phase difference is plus, means it is leading. Current is leading, means if the potential is say pi by 2, the potential is maximum, current is say ahead by 90. If the potential is 0, current ahead by pi by 2, so leading. So this shows that substituting the value, if I can write E naught over this, if I write E naught over 1 over omega c as I naught, then I is equal to I naught and sin omega t plus pi by 2. So this what is now phase shift? We can consider here that phase shift. Phase shift means in the voltage and the current. Phase shift. I naught sin omega t plus pi by 2. So this is the equation 3. Means you see the equation 3 and equation 1, but with the potential, then we see that if we compare equation 3 with equation 1 of EMF, we see that EMF, we see that current has a phase difference of pi by 2, means current leading the potential by 90 degree or pi by 2. The phasor diagram shown in figure, I can show the phasor diagram. This can be represented by phasor diagram. What is the phasor diagram? So we have, this is the potential and this is the current. Zero is this is the potential represented by here this is a 90 degree. This is the this is the potential E. This is the current I. Means current is positive plus, because this is the circular motion of the phasor diagram here, starting from here. So this is anti-clockwise. So this theta increasing, theta. So that way the potential is lagging behind, or current is leading behind, current is leading ahead by 90 degrees. So that is the phasor diagram. Phasor for E and I. How we can represent the E and I in terms of phase. So this gives us that phasor diagram, that current leads the potential by 90 degree. Also what we can write, second point we can write, as we have in the inductance case here, the capacitive reactance. As we have in the inductance case, inductive reactance omega L, here you see, when you see the expression of the current, that is the I naught is equal to E naught over 1 over omega C. So current is potential divided by the resistance. So for the capacitive circuit, 1 over omega C is equivalent to a resistance offered to flow of current. So that is 1 over omega C behaves like this is called capacitive reactance. Means you can write just omega 1 over omega C equivalent to resistance. So reactance, that is capacitor. In the case of capacitor, 1 over omega c. It behaves like a resistance in the resistance circuit. Means for the potential, it is just like resistance, means 1 over omega c is more, current will be less. 1 over omega c is less, current will be more. So 1 over omega c behaves like reactance. That is E naught over I naught. You can write E naught over I naught. That is like resistance. For capacitor circuit, this resistance is equal to 1 over omega c. That is the capacitive reactance called, or resistance for the capacitor circuit. Potential upon current is the resistance. Okay. Third point, this is second point. Third point also we can discuss is well, the symbol notation for this is Xc. For inductance it was, you say omega L was written as XL, that is inductive reactance. Similarly, Xc is 1 over omega c is capacitive reactance. This is the representation. So it is represented by Xc, XL, like that. So third point I want to say is average power for a capacitor circuit. We can write E is equal to E naught sine omega t, and I is equal to I naught sine omega t plus pi by 2, and that is a power, instantaneous power at any moment, instantaneous power is a P, instantaneous power, EP is equal to E into I. At any instant, E potential, I current, so E into I is the instantaneous power. That is a E naught sine omega t into I naught sine omega t plus pi by 2. So this is instantaneous power. That means E naught, I naught, sine omega t plus pi by 2 is cos omega t. So sine omega t, cos omega t, in terms of sine 2 omega t, we can write this as E naught over I naught. The P is equal to, instantaneous power is equal to E naught, I naught, and this sine 2 omega t divided by 2. So this 2 we can write here. This is the instantaneous power. And average power we write by capital P. So this is average power, means integral over, say, time, from 0 to time means full, one complete cycle, and then this is divided by, say, time, and then E naught, I naught by 2 sine 2 omega t. So this you can write, that P is the, this you can say this will be 0. Integral of this in the limit. The value of just like that. Average power P over one cycle means 0. This is also true for inductance. Why? Because for half positive cycle, inductance was opposing the growth of current, and for the negative, inductance was giving the power from the magnetic stored energy. Here also, capacitor once is charging, and then for the negative part it is discharging, means so charge collected and charge flow. So that means total power is 0. For half cycle is the positive, for half cycle negative. So total capacitive power average for one full cycle is also 0, just like inductance case we have. So average power in the capacitor circuit, average power in the inductor circuit, all are 0. So now we have an article of, say, AC circuit containing R and L in series. Means now R and L are connected in series together, and then AC source is applied. So what we have? We have a circuit of, say, R and L connected together to AC source. Of course, we can have a key just to put off and off circuit. So E is the source, E is equal to E naught sin omega t. And this is now R, this is now L. So R, L and series, we have here, say, across resistance, the potential is VR, means between these 2 points, and here, from here to here, we have potential VL across, or you can go up to here, no problem, same point. So here potential drop VR, here potential drop VL. So these are two potentials. Now what we can write? So we can write, say, EV RMS or average value of potential, EV. IV similarly RMS value of the current, RMS value of the current, and VR and VL. VR is the potential drop across, say I is the current in the circuit. So VR is IV into R, and VL is IV into omega L. Omega L is the inductive reactance, that is resistance of inductance. Or omega L, or we also write IV into XL. XL is the omega L. XL is omega L. So, what we have? EB is equal to, you see here we have inductance and this I, inductance and the potential VL, potential across inductance. So current was lagging behind 90 degree. So VL is here vector, IL is like this. So these are two representations of 90 degree current is lagging behind. And we know that this is a vector diagram of potential, say VL 90 degree, IV, and then this is a VR here. This is a VR and this is a EV. That is two potentials, VR plus VL. This is VR is in line with the IV, no phase difference, and VL has 90 degree phase difference. So this is by side is the vector potential, and this is X side is the potential across resistance. That is the resistance potential and inductance potential, they have 90 degree phase difference. So this means this two vectors are 90 degree, this is also 90 degree. So two vectors are 90 degree. So this is square plus this is square equal to EB square. Then you can write that the square of two vectors very easily. So that will give you the value of EB. EB is equal to VR square plus VL square, and that is under root of this. Because these are triangle, this is a right angle triangle, the two vectors of inductance potential and resistance potential. This VR is in phase with the current, so no phase difference, and VL has 90 degree phase difference, means current lags behind. Because when current starts increasing, inductance opposes the growth, back EMF. When current decreasing, inductance gives the charge from stored energy, magnetic energy. So that is the current lagging behind 90 degree. But this is now the EB value for the case of inductance and resistance. The value of EB. So that is you have EB is equal to VR square. VR is IVR square. So this is the IB square R square plus IB square XL square 1 by 2. So this means you can take out IB outside, and then you can write this is simply IB outside and R square plus XL square 1 by 2. So EB over IB you can write, or IB is equal to EB over R square plus XL square 1 by 2. So current is potential divided by this. This is now reactance of RL circuit, you can say, and this is called impedance in fact. So R square plus XL square, R square plus this R square plus XL square 1 by 2. This is called impedance, or this is the resistance in a crude language, non-scientific language you can say. This is resistance of RL circuit. This is called impedance, represented by symbol Z. Z is the impedance. Is equal to R square plus XL square 1 by 2. This is for inductance and resistance circuit. So what does it mean? Now we will have some more discussion that will be say phase angle. We want to calculate the phase angle between voltage and current. What we can write? Say if EB phi is the phase angle, means the vectors there. What was phase angle means? This is the 2. So this is the phase phi. This was the VR. This was the VL. So what the phase difference? And we know that this is 90. This was the current. IV. So this is some point we will write O, A and V. So what is the phase angle between the resultant? Say we have say EB is equal to a phase angle tangent phi. Tangent of phi. This upon this. That is a VL over VR. Tangent VL over VR means IB XL over IB R. IB cancel, so this is XL over R. The phi, tangent phi. So that means that phase angle, that is the tangent phi given by this angle. So what we can write? Since the values of XL, XL and R are known, because they are circuit elements, they are known, the value of phi can be calculated, of course. The value of phi can be calculated. So phi can be calculated. The wave diagram shown in the figure represents we can represent the wave diagram here. This is 0. This is omega t. And here we have say So this is the E. E is changing this. And what the I? That is the phi is the phase difference. Say, suppose phi is here. This angle. This is much different time difference. So means this starts from here. And then so this is the value difference because of phase angle. This is the phi angle. Means when the time has reached this point, due to the inductive opposition of back EMF, current lags behind. If it is only inductance, it is 90 degrees. If it is inductance plus resistance, it is phi. And that phi, it is not 90, it is some value given by XL over R. Tangent is given by XL over R. So this is the phi here. Phi. This is see, pi by 2, pi, 3 pi by 2, 2 pi. Here this pi by 2, pi, 3 pi by 2 and 2 pi. So the phase difference is given by XL over R. And we have already given the impedance. Well, this also can be called impedance triangle. You can call this as impedance triangle. This is the VR, this is the BL, and this is the E or the potential EV. So this is the potential triangle. Similarly, you can make from this impedance triangle, means here the resistance R, here is omega L, and here is the representative impedance of the total circuit by simply Z. So this is also impedance triangle, means here it is R, here it is X, L, and here it is Z. So this also you can say impedance triangle. And friends, we can stop today now here. Maybe next time when we meet, we will be discussing say R and C circuit, and then R, L and C circuit together. So thank you very much for listening to me.